Okay, so now that we've talked about how to do double and triple integrals over volume regions and area regions, there's one more type of integral that's extremely important, and that's just single integrals over curves. So if you think you have volume regions like this, so here's some volume, here's some area. So here we're going to do triple integrals over the volume, break it up into little volume elements. Here we're going to do double integrals over area regions. So functions over area elements. So in other words, we break up the area into small pieces, and then we just add up all the function values on all these little area elements. We do the same thing here, except of course we break it into little volume pieces. So the last thing we want to talk about, like I said, is line integrals. So if we have a line, or a curve rather, and now this could be in the plane or in space, so we'll call this curve C. And now we want the curve to be oriented. We discussed this a little bit when we talked about vector valued functions. But specifically, another way to think about an oriented curve is it's a curve given by some parameterization. Or in other words, we have a vector valued function like this, r of t, that gives this curve, and it gives it an orientation. And I like to stick to the physical representation of this. I want to think about this as the motion of the particle moving along this curve C. Okay, so what we can do is we can break up our curve into little tiny pieces like this. And if you remember, this is really how we found the arc length of the curve, or the distance that the particle travels. We broke it up into little small pieces and then added up all of those pieces. But now what we can think about is we can think about having a function that's defined on the curve C. So sort of like when we had a function defined on this volume region V, or a function defined on this area region A. So we can actually just think about a function defined on this curve C, and then for all of these small little pieces, and now these small little pieces here, I'm going to call ds, so they're going to be just kind of elements of the curve, or small little length elements. So here we had volume elements, here we had area elements, now we'll have little length elements pointing along the curve. We can take the function value at that point, so f of x, y, z, and we can just multiply it together. So we can take the function and multiply by the little piece of the curve, ds, the length element, and then we can add all of those up. So the line integral of this function f over the curve C is as follows. Okay, so now what we want to think is that we have a starting point, t equals a, and an ending point, t equals b. So that's sort of like the domain of our vector value function. So what we do is we say the line integral of f over c is, well, it's the integral over the curve C of our function f over these line elements, ds. Okay, so that's not super enlightening, that's just kind of a notation. Now normally when we have this oriented curve, we have a parameterization. So another way to think about this vector valued function that's giving us this curve, we've said before, is that it is a parameterization of the curve. So if we have a parameterization of the curve, then we can actually write this as the integral from t equals a to t equals b of f of, well, f is a function of x, y, and z, but I can sort of input in x of t, y of t, and z of t. So this is kind of like the chain rule. We've seen this idea before. And then what I want to do is I want to multiply by the derivative, specifically the magnitude of the derivative, or you can think about the speed of the particle, dt. Okay, so this should look pretty familiar. We talked about what happens when we integrate just the speed of the particle. That actually gives us the distance. And so just like when we integrated just the volume element over the volume, we got the volume. And we integrated just over the area elements of the area, we got the area. In other words, if we take our function to be 1, we just get the volume of area. So if this function is just the function 1, then we really will just get the arc length of the curve. So this is the general form of a line integral. And now I should mention that it's really an example of the first type of line integral that we'll talk about. So this is really the first type of line integral. And what's special about this type of line integral is the function that we're integrating, this f, right, so the integrand, is a scalar valued function. Meaning that I'm really just adding up a bunch of numbers. So at each little line element, the function has a number there, and I'm just taking that number and then adding up all of those numbers over all of the pieces of the line, all the line elements. And then this is just sort of what happens when I have the parameterization. And it's coming from the fact that ds really is like a change in t along the tangent direction, like that. So the length that I move along the curve from this parameterization is just the absolute value of the derivative and then times a little change in t. Okay, so the thing to take away is that this is the first type of line integral, and it's really the line integral of a scalar valued function. And so next, after we look at a couple of examples, we'll talk about the second type, and that'll be line integrals over a vector field. So kind of like with doing triple integrals over volume regions or double integrals over area regions, I want to give you just a very concrete example of when you would do a line integral. So let's say we have a piece of wire, and it's kind of bent into this curve shape like this. So the wire is bent along the curve. And let's say that the wire has a linear density. This is just going to be exactly like the volume density or the area density. So the linear density, but we're going to use lambda. So we use sigma for area density, delta for volume density. We don't really need to use a different letter here, but we'll use lambda for linear density. Okay, so the linear density is lambda, and this is really like mass per unit length. Okay, and of course the linear density doesn't have to be constant. Now if you pick up any piece of rope that you can find, most rope has a constant linear density, meaning that if I take any small piece of the rope, the density is going to be the same. But it is possible that this wire that's bent in the shape like this has a density that depends on where I am on the wire. Maybe it's more dense on one end and kind of dwindles out and becomes less dense on the other end. Okay. So let's say I want to find the mass of this piece of wire. Okay, so what I want to do is, and this is really standard for doing line integrals, the first step is typically always to give a parameterization of the curve. So this is something that we have a little bit of practice doing before, but it's going to be worth looking at some examples and doing some practice how to parameterize a curve. Because the first step in doing a line integral is going to parameterize the curve. And what do I mean by that? Well, I want to give a vector valued function, r of t, for t between, say, a and b, that traces out this curve. So this is like t equals a down here, and this is t equals b. And then, for any time in between, this will be r of t. So remember, r of t is just tracing out the curve. And here we're using t, and we could think about this as being the path of a particle and t being time, but here, it's just, t is just a parameter, really. T is the parameter that's kind of tracing out the curve. Okay, so once we have a parameterization of the curve, r of t, then what can we do to find the mass of the wire? Well, we just add up the mass elements. And the mass elements are dm is, well, you take a small piece of the wire ds and you multiply it by the density there. So dm is just lambda times ds. Okay, so then the mass, we'll say m, is the integral from, well, it's the integral over the curve. We'll just kind of write symbolically what we're doing here, and then we add up the mass elements. Well, that's the same thing as just integrating over the curve the function lambda along these length elements. So a length element times its density gives us the mass element. But since we have a parameterization, the reason we found a parameterization is because we can actually write this in a form that we can evaluate just as a single integral. So the integral from a to b of lambda of x of t, y of t, z of t, and then, of course, we multiply by the derivative, or the absolute value of the derivative of the parameterization, and then we have dt. Okay, so that's how we would find the mass of the wire. Given a linear density function, we parameterize the curve, and then we just add up all of these mass elements. Very similar to finding the mass of a volume element. But notice, the thing that comes up is this sort of absolute value of the derivative of the parameterization, or you can think about it's the speed if this is representing the motion of a particle. And we're sort of weighting the integral with this factor, and this is a very important factor. And what it's really doing is it's allowing us to kind of give a better description of what this ds is in space. So ds is just kind of a little piece of the curve, but what it really is sort of a little change along the tangent line of the curve. And since we have this parameterization, this is what a change along the tangent line looks like. So without getting into too much detail, that's what's going on. All right, so I already mentioned that there are two types of line integrals, and we already did the first. In the first type, the line integral of a scalar valued function is just a natural extension of what we did with double and triple integrals. But instead of integrating over a volume region or an area region, we're just integrating over a curve. So it's kind of the one-dimensional analog of what we did before. I don't want to say that the second type of line integral is more important, but it might be more important. And that's the line integral over a vector field. And this line integral is going to have, we're definitely going to talk about more applications of this type of line integral. But before we can talk about the line integral over a vector field, we're going to have to say what a vector field is. So what is a vector field? And we're going to keep this really simple. And I claim that actually we've already seen a couple different types of examples of vector fields. But here we're going to give kind of the most general version of what a vector field is. So in layman's terms, a vector field is a rule or a function that assigns to each point in space, or we can have a similar definition in the plane, a vector. So that's kind of the the general idea. Now formally, what is a vector field? It's a function from, say, R2 to R2 or R3 to R3. So the very first examples of vector valued functions that we talked about, we were looking at functions, say, from R into R3. So somehow we were taking the real line and tracing out a curve in R3. So this was like a vector valued function, just as an example. Now actually, a vector field is another type of vector valued function because the output is a vector. But a vector field we really want to think about is the input being more than one variable as well. So now we also talked about multivariable functions, something like this, where you're taking maybe 3 variable input and outputting a number. So this was like a multivariate function. But for a vector field, we really want to think about you're taking in multiple inputs and outputting vectors. So this is kind of what we want to think about with a vector field, just to sort of tell the story of kind of what we've been doing. We spent some time talking about vector valued functions, then we spend a lot of time talking about multivariate functions. Now both of these are going to play a role in what we're going to talk about next, but vector fields are just kind of the next step in the story, where we have, we're in space and we're outputting vectors at each point. And if we think about this physically, so I'm going to draw a vector field in the plane. So I said that a vector field is a rule, or it's really a function that assigns to each point, in this case in the plane, a vector. So let's denote our vector field by F. So we'll typically use capital letters for vector fields, and again with arrows over the top just to signify that they are outputting vectors, just like with vector value functions. And so what does F look like? Well, a typical vector field, F, is going to look like this. So every point, I draw an arrow. I have a vector. So at every point in space, or in this case the plane, I have a vector. Okay. And so you can sort of draw this all day. Every point, I have a vector. So what in the world does this have to do with anything? Well, vector fields are extremely useful in it, and they model a lot of different things. So let me give you a couple of examples. So this vector field here could represent, let's say I'm a leaf sitting on the surface of the water. So I'm here. And then what these arrows are telling me, what my vector field is telling me, are the forces that are pushing me along the water. So maybe I'm right here, and there's a vector here pushing me in this direction. And then I get to this point. There's another vector that pushes me in this direction. And then I get to this point. There's another vector pushing me in this direction. And so these arrows are really like forces on the water. And now the same is true if I'm in any force field, if I'm in a gravitational field. So we live in a vector field. And right now, just sitting here, I'm in a vector field. So at every point in space, there is a sort of imaginary arrow pushing down due to gravity. That's the gravitational field. That's a vector field. Electric fields are an example of vector fields. So if I'm an electron, then in the world around me, there are electric fields that are applying forces on objects that have a charge. And so at any given point, that electron gets acted on by a vector field. So hopefully that's kind of a snapshot as to what a vector field is and how it can be useful. And what we want to do is we want to use vector fields to describe how things move in space and in the plane. And of course, there's a lot of other examples too. But the general form, I'll just say before we kind of move on and talk about line integrals over vector fields, is that a vector field has this general form. So in the plane, a vector field, like I said, it is it's a function that has multiple inputs. So let me write the inputs. So in the plane, I'll take in two inputs, an xy point, and then what I'll do is I'll output a vector. And so I'm going to have two component functions. So I'm going to have an x component function that I'm going to denote p of xy, and then a y component function that I'm going to denote q of xy. And now p and q are scalar valued functions. So I take in an xy point, p gives me a number, and q gives me a number, and those become the components of my vector field. So these are my output arrows. So for every xy point in the plane, I get a number for the x coordinate, I get a number for the y coordinate, and that gives me my output vector. Now if I have a vector field in space, I'm going to input three numbers, x, y, and z, and I'm going to have three component functions. So I'm going to have p, and p is going to depend on all three variables, x, y, and z in general. And then I'll have q, and then I'll typically just use an r for the third component function. So again, for every point x, y, and z in space, if I have a vector field f, then I have an x component function, a y component function, and a z component function, and I'm outputting a vector at each point x, y, and z. So that's the idea of a vector field. And we'll talk more about vector fields in the next topic, but for now, that's the definition. It's just a function, either say from R2 or R2 or R3 or R3. I'm taking in a point in space or the plane and I'm outputting a vector there. How can we think about that? Well, the best way is to think about forces. Force fields are examples of vector fields. We live in vector fields. They're everywhere. So hopefully that'll get you primed for what's to come. Okay, so real quick, I want to remind you that we've actually already discussed a type of vector field, and I would say it's probably the most important example of a vector field, which is great. If we've already talked about the most important example of a vector field, then we should already be in the game. So again, just imagine that I have a function of 2 variables. I could do something similar if I had a function of 3 variables, but just to help visualize things, let's take a scalar valued function of 2 variables. And so recall that I can plot the level curves of f. So maybe my level curves look something like this. I don't know, something like that. So here are my level curves of f. You know, we have our typical topographical map or mountain, you know, however you want to think about our level curves. Hopefully by now you're getting used to this idea of, okay, what this is and how this represents f. So what we have is what's called the gradient field. Here we go. So maybe you already made this connection, but the gradient field, gradient of f, is a vector field. And hopefully now this is clicking. So why is it a vector field? Well, because what is the gradient? The gradient for any point in space, I get a vector pointing uphill, like that. So for any point in space, I have a vector showing me where uphill is. So I'll draw a few examples. Okay, and literally any point here I can pick, I have an arrow. It's pointing me uphill. And so recall that, you know, just to kind of think about our previous description of what a vector field is, it is a vector valued function. So the x component function is the partial derivative with respect to x. And then the y component function is the partial derivative with respect to y. And of course I can do the same thing if I had a function of 3 variables. The gradient field of a function of 3 variables is a vector field. And in fact, the gradient field of any function is a vector field. Okay, so this is a very important example, and hopefully it kind of gives you a little bit of comfort to see that, yeah, this isn't such a new idea. We have, you know, an example of our gradient. It's just giving us arrows. And those arrows actually mean something. And typically that's going to be the case. We're not just going to consider random vector fields with vectors going all over the place. They're typically going to represent something that you may have seen before. And you'll see more of that as we go along. All right, so now we're ready to talk about the line integral of a vector field over a curve. All right, so let's just kind of give some setup. So let's suppose we have a vector field, f, and we'll just say it's in 2 dimensions. Of course, everything I'm going to say will apply to 3 dimensions as well, but it's a little bit easier to visualize things in 2 dimensions. So let's maybe just sketch what our vector field might look like. So just have a bunch of arrows, maybe I'll kind of give it some feel for what it might represent. So you see that there's kind of a motion to this vector field. These arrows shouldn't be bent, but there we go. Maybe some more down here. Okay, so here's an example of a vector field, and you see that this might represent some sort of wind blowing. You know, so if I'm here, I'm kind of getting pushed this way. If I'm here, I'm kind of getting pushed this way. So you can just imagine that maybe this is some kind of force field, or maybe it's an electric field or something, where the arrows are sort of showing you where things are getting pushed in the vector field. And that's a really good visual way to think about vector fields. Okay, so now within this vector field, suppose that I have an oriented curve like this. Okay, and it's going to be oriented. So let's give it a name. C is an oriented curve. All right, cool. And now, again, let's say that we have a parameterization of C as an oriented curve. So C is really going to be given by some function r of t, which is just x of t, y of t, since we're in the plane. Okay. And now we really want to depend on kind of a physical analogy here when we talk about the line integral. We really want to think about the curve being the path of a particle. So this is really the path of a particle here. So here's maybe t equals a, that point, and this point we'll say is t equals b. So it's starting here, and then it's going along and ending here. Then what we want to define is, or I guess what our motivation could be is, well, the work done by this force field on the object. So if you look, let's say right here. So right here on our curve, recall that we have a unit tangent vector that we'll just call t with the arrow. So this is a unit tangent vector pointing along the direction of motion in the curve. So basically at this point, this arrow is just pointing where I'm going. It's a direction vector. It's a length 1 vector. And since we have a parameterization of the curve, recall that we actually have t, big T, the tangent vector, as a function of t. And so what is it? Well, it's r prime of t divided by the length of r prime of t. Okay, so just a little bit of review there. And so we can think that the work done by this force field is, okay, so we're at this point, and I have a force that's pushing me this way, but I'm actually going this way. So the work that the force field does on the particle moving is the dot product of the force vector field, vector here, and the direction of motion here. So that's how we're going to define our line integral. That's going to motivate the line integral definition. So the line integral and again, it's the line integral of a vector field over an oriented curve or a parameterized curve C is, well, it's an integral over the curve. And I can't add up function values like I did with the line integral of a scalar valued function. What I'm actually going to be adding up is the contribution of the dot product of the vector at the point and the direction I'm moving. So it's sort of just adding up how much of the vector field is moving in the direction of motion of the curve along the point. So what we have is that it's F dot T ds. And so again, we're going to break the curve into little small pieces, little line elements. And then for each one of those line elements, what are we going to sort of multiply by? We're going to multiply by the amount of the vector field that's lying in the direction of motion. Okay. Or in other words, how much is the force helping us move in that direction is what we're adding up. Okay, so since we have a parameterization, okay, this is just kind of notation for the line integral. We're just adding up all of these dot products. Well, since we have a parameterization, we can write the integral as the integral from a to b of what? So I'm going to take my vector field, f, okay? And so recall that the vector field, we're going to evaluate at the point r of t. And now what do I mean by this? Well, I mean that recall that f is really going to be a function of x and y. So when I write f of r of t, sometimes this is shorthand notation just to avoid writing all of this, but what I mean is f of x of t, y of t, like that. So I have that, and then I'm going to do the dot product with r prime of t. Okay, and so notice, okay, so that's f, and then I have the unit tangent vector. Okay, and I'm going to be dividing out by this r prime of t, the length of r prime of t. So that's really it. And then I have dt. So this is the line integral of this vector field over this parameterized curve. And now there's another way to actually think about this, okay? So if you remember the chain rule, this is basically what the chain rule says. So if this vector field were the gradient of a function, I mean, this would be exactly the chain rule. So just write down what the chain rule says. So basically, we're just adding up the little changes of the vector field with respect to t. But I mean, that's only in the case where the vector field is actually a gradient field. So that's not always going to be the case. But this is always what the line integral is equal to when we have a parameterized curve. So as I already alluded to, one of the primary applications of the line integral of a vector field over a oriented curve is the work done of a force field, if the vector field is a force field, done on a particle as it traces out a curve, or as it moves, either in the plane or in space. So if we think about a little work element done by, okay, so we have a vector, so a force field, specifically F. I mean, it's a vector field, but we can think about it as actually representing a force field. And we have an oriented curve C. Then the work done by F on C, or on the particle moving along C, more specifically, is, remember, work is a dot product. It really is just, okay, it's F, and then we just take the component of F that's along the component of motion, like that. Okay. And then we multiply by this ds, and the ds is there just to signify, okay, well, we're taking a small, we're not just taking a unit step, we're just taking a small differential step in the tangent direction and then adding up the component of that force. And so this gives just a work element in terms of a line element multiplied by, basically just the component of the force that's in the direction of motion. So that's just what work is. It's F dot displacement. So that's what this is saying. It's just F dot with, the direction vector times a small change in that direction. Okay, and then if we want the total work done on the motion of the particle moving along this curve by the vector field, then we just add up all of these little work elements. And of course, what we get is exactly the line integral. And so again, I mean, the first time you see this notation, it's sort of formal. It looks kind of like, oh, what is going on? But remember that this doesn't really mean anything until we give some sort of parameterization of the curve. Once we have a parameterization of the curve, we sort of actually just fill in the blanks here and actually write in what this is. So what this really ends up being is, well, what we really mean is the particle moving from, time equals a to time equals b. And this is where we actually just fill in, okay, so we compose the vector field with the position of the particle, and then we do a dot product with the derivative. And that's dt. So of course, yeah, once we have a parameterization of the curve, we can actually write it in a way where, okay, this is actually just a scalar valued function in here that we're just doing a standard Calc 1 one variable integral with respect to the parameter t, which we're typically thinking of as time. And again, this is the total work done by F on, so I'm going to say on C, but really I mean on a particle moving along C. Okay, so we've now addressed the two major types of line integrals. So we have the line integral of a scalar valued function f over a curve C. And then we have the line integral of a vector field over C. So actually, there's going to be two special cases of a line integral of a vector field over C. And that's the case where the curve C is three things. So if C is simple, and I'll tell you what all these things mean. Closed and positively oriented. Okay, so over here, let me tell you what all these things mean. So simple means non-intersecting. And then closed means we start and end at same point. And then positively oriented means the orientation is counterclockwise. Okay, so let's give some examples and non-examples. So here is an example. And we want to make sure that the orientation is counterclockwise, like this. So notice that this curve does not intersect itself. It's closed, so if it starts here, it also ends there. And it's positively oriented because it moves counterclockwise. So that's our example. So our non-examples, so here's a curve that's not simple because it intersects itself. So not simple. Of course, we could have something like this that's not closed. And then finally, we could have a simple closed curve that's actually oriented clockwise. So this is negatively oriented. Okay, so hopefully that's clear. Simple, closed, positively oriented. It doesn't intersect itself. And now I think we talked about this a little bit when we talked about parameterizing curves. I mean, we also want it to be what's called piecewise smooth, but we've kind of been assuming all of that from the beginning. Okay, but I mean, it's just a loop. If it's like a circle, maybe with a little bit of bend here or there, but not enough that it intersects itself. Okay. So if C is a simple closed, positively oriented curve, then we actually get two subcases. So we get what's called a circulation integral, and then we get what's called a flux integral. Okay, so we're going to spend a little bit of time talking about what both of these are. But the idea is, okay, so we first talked about line integrals of scalar value functions over oriented curves. Then we talked about line integrals of vector fields over oriented curves. Now specifically here, when we have a line integral of a vector field over a closed, simple, positively oriented curve, we can also talk about a circulation integral over C and a flux integral over C. So let's talk about what those mean specifically. All right, so the first type of special integral that we want to talk about is a circulation integral. And really, there's not a lot of new content that we're going to talk about here. The only distinction I'm wanting to make is that a circulation integral only comes up when you have a closed, simple, positively oriented curve. So that's the setup. So we have a vector field, F, and we have a curve C that's simple, closed, positively oriented. Okay, so let's just draw what's going on here. And I'll say that it really makes the most sense to talk about circulation integrals in the plane. And the same thing for flux line integrals. So we're really going to narrow down to just talking about vector fields in the plane. So a vector field in the plane is just a rule that assigns to each point in the plane a vector like this. So all over my plane I have a vector, but again, you can think about this as like the surface of the water. So the water is just kind of has ebbs and flows, and it's moving, it's applying forces to whatever's in it and causing things to move, or maybe something's moving in it. The force field of the water is doing work, etc. All of the ways we have to sort of conceptualize a vector field. And what I have is this curve. And now the curve specifically, I want it to be those three things: simple, non-intersecting; closed, meaning that it has a start point and an end point; and then it's also positively oriented. So the orientation will be counterclockwise. So actually this way. There we go. Okay, And so the circulation integral, I mean, all I'm really doing is just introducing some notation, because when I tell you what the circulation integral actually is, you're going to be like, wait, but what are you telling me? Okay, so I'm introducing this new notation, and I'm putting this circle around the integral sign to signify that the line integral that I'm taking over this curve C is over a curve C that is simple, closed, positively oriented. And so from there, I'm just going to write in the line integral. Okay, so this is just notation, but all I mean by this is just the line integral. But I'm going to reserve this notation, and I'm going to use this notation when I really want to highlight the fact that this is a line integral over a simple, closed, positively oriented curve. But it really is just the line integral. I'm just giving it a new name. But this is going to be a very important application, is when we have this sort of situation, the simple, closed, positively oriented curve, there's going to be a lot of really good applications, and it's really going to illustrate the idea of sort of the fundamental theorem or theorems of vector calculus that we're moving towards. Okay, so the next type of special integral we want to talk about is actually a little bit different than the circulation integral. So the circulation integral basically was just a line integral over a simple, closed, positively oriented curve. So the next integral that we're going to talk about is a flux integral. And this really will be a little bit different than just a typical line integral. And you'll see what I mean. But the setup is exactly the same. We have a vector field, and we have a curve that is simple, closed, positively oriented. So let's draw a picture again. And so we have our vector field, whatever it looks like. All of these arrows pointing all over the place. Maybe there's some method to their madness, but there's our vector field. And then we have our simple, closed, positively oriented curve. So it's oriented this way. Okay, and so the idea behind the circulation integral, sort of the physical interpretation, is what we're really doing is we're adding up how much of the vector field sort of rotates around the boundary of the curve, like this. So you can think about it kind of like, how much rotation is in the vector field? How much is it spinning sort of around this curve, like that? The flux integral is going to be completely different. Okay, so the flux integral, let me just tell you what it is first, and then we'll talk about what it means. Again, I'm going to use this notation to signify, okay, well, this is a sort of line integral over this simple, closed, positively oriented curve. But instead of taking the dot product of the vector field over the tangent direction, so it's basically looking how much, of the vector field lies along the tangent direction, like that, I'm actually going to do the exact opposite. I'm actually going to think about how much of the vector field lies over the normal direction. And so where does the normal direction point? Well, it points perpendicular to the curve, like this. And I'm doing the dot product, so I'm really seeing how much of the vector field is leaving this bounded region. So I'm taking, instead of taking the dot product of the vector field with the tangential direction, or in other words, seeing how much of the vector field is kind of going with the flow, going with the direction my particle is traveling, or going with the curve, I'm looking at how much is going across the curve. Okay, and so you're probably thinking, well, what is this? I mean, this is more or less just notation. Now I'm using this kind of hat notation to signify that this is just a unit vector in the normal direction before we had the tangent vector, or unit vector in the tangent direction. And so I can actually write this in terms of the tangent direction. So what this really is the, sometimes this is called a contour integral. Just, I might say that from time to time. So this integral over a closed, simple, positively oriented curve. So what I can do is I can say, all right, what is the normal direction? Well, the normal direction points out, and the curve is positively oriented. Okay, so if I want the normal direction, what I can do is I can actually do a cross product. Okay, so let's think about this. So if my direction of my curve is pointing this way, and I want a vector perpendicular to the curve, what I can do is I can look at t. So I can look at my vector t, unit vector pointing in the direction of the curve, and I can take the cross product with k, a unit vector in the z direction. Okay, so just do kind of your right-hand rule if you forgot about that, but if I point in the tangential direction and curl towards the positive z direction, or out of the page towards me, my thumb points normal and out of the curve. So what this really is f dot the tangent direction cross k, a unit vector in the k direction. And of course, these integrals are over line elements ds, like that. Okay, so again, what's the name of the game here? Well, I want to parameterize my curve, and once I have a parameterized curve, well, I can actually express the unit tangent vector as a function of t. I can express this as a function of t. I can just do this cross product, and I'll get a normal vector as a function of t, and then I just have my typical line integral. But it's a little bit different because I'm doing the dot product instead of with the tangent direction, actually with the normal direction. And physically, the interpretation is very important. So if we think about this as a fluid, then along this curve, the circulation integral gives how much the fluid rotates. Well, the flux integral is giving how much the fluid is sort of moving out across this boundary, or how much it is rippling out across the boundary. So that's the picture that I want you to have in mind as we go forward when we talk about circulation integrals and flux integrals. All right, so we want to find the mass of this wire that's bent along the upper semicircle of x squared plus y squared equals 1. Okay, so this wire is going to be bent along this semicircle like this. Really, the semicircle is square root of 1 minus x squared. All right, and then the linear density is just equal to y. Okay, so it's less dense closer to the ends over here, and it's more dense up here. We want to find the mass. Okay, so what is the mass? Well, the mass is the line integral over this curve of the scalar valued function, which is the density, and then integrated over these line elements, ds. And so as we said, this is very difficult to do until we actually have a parameterization of the curve. So we need to give a parameterization of the upper hemisphere, given by this here. X squared plus y squared equals 1. So the easiest thing to do is just, well, this is just a piece of the unit circle, so we can just use cosine t sine t. And then instead of letting t going from 0 to 2 pi, we'll just stop t at pi. So we'll go from 0 all the way to pi. And this is a parameterization of this curve. C, right here. All right, great. So then we can sort of fill in the details here. So we're going to be integrating over this curve the function y ds. And now y, now let's plug in everything in terms of t. So this is the integral from 0 to pi, because t is going from 0 to pi. And then y is sine t. Okay. And then I need to multiply by the length of the derivative. But notice that the derivative is minus sine t cosine t, but the length of this is sine squared plus cosine squared, which equals 1. So this is just 1 dt. Okay, well this is great. So we just take an antiderivative. That's going to be minus cosine t. And then we evaluate from 0 to pi. And this is something I think we've done plenty of times before. We're going to get 2. So the mass of this wire is 2. All right, so now we have a line integral over a vector field. So we're given a vector field, and we're given this oriented curve, given by this parameterization. And so recall that the work done by a force field on a particle moving along a path is, well, I add up all of the work elements. Okay, and what is a small work element? Well, I take the component of the vector field that lies in the tangential direction, or in the direction of motion, and then times a small little change along the tangential direction, like that. Okay, and that's along the curve, of course, that's given by this parameterization. And since we have a parameterization, we can actually write this out as the integral from 0 to 1 of f evaluated at r. And so recall what that means. I'm just going to plug in x of t, y of t, and z of t for x, y, and z. And then we take the dot product with the derivative. And then dt. Cool, so let's write down what all of this is, first of all. So here's our integral. What is f of r of t? Well, we're just going to plug in x of t in for x, y of t in for y, and z of t in for z. So this is equal to cosine of x, which is t cubed, then sine of y, which is t squared, then t, okay, so then y times z is t cubed. Okay, and then the derivative, or prime of t, is what? Let's see. 3t squared, and then 2t, and 1. All right, so then what is f r of t dot r prime of t? Well, this is 3t squared cosine t cubed plus 2t times sine t squared, and then plus t cubed. So this is the function that we're integrating from 0 to 1. So the work done is the integral from 0 to 1 of this function. 3t squared cosine t cubed plus 2t sine of t squared plus t cubed. All right. So we're actually really lucky here, because if you notice, if I want to take an antiderivative of this, well, this 3t squared is the derivative of t cubed. So the antiderivative of 3t squared cosine t cubed is just sine of t cubed. And similarly, an antiderivative here is just negative cosine t squared. Just notice, just take the derivative. It's set up nicely to do use substitution. And then an antiderivative here is t to the 4th over 4. And we're evaluating this from 0 to 1. So sine of 1 cubed, that's just sine of 1. Okay, and then minus sine of 0 is 0. Then we have minus cosine of 1. So minus cosine of 1 squared. Then a minus cosine of 0, so plus cosine of 0, which is 1. And then t to the 4th over 4 evaluated from 0 to 1 is just 1/4. So whatever this number is, that's the work done by this force field on the particle moving along this path. All right, so we're going to do a circulation integral. And recall that this really is just a line integral. In the closed, simple, positively oriented curve that we're going to be integrating over is this triangle. So let's plot this triangle. So we have the point 2, 0, and 2, 2, and 0, 0. And now notice we have a positive orientation, so that's going to be counterclockwise, so that'll be this way. Another thing to notice is that really here we have 4 pieces. Sorry, not 4 pieces, we have 3 pieces. We have this first kind of segment that we'll do a line integral over, then the second piece, then this third piece. And so the total line integral or circulation integral is going to be the contribution from this piece plus the contribution for this piece plus the contribution for this piece. Okay, so recall we know how to do line integrals. So let's start with the first piece. We need to do the line integral over piece 1 of, okay, so we take the vector field and do the dot product with the tangent direction, ds, And so to really actually evaluate this, we want to give a parameterization of the curve. So we might as well just go ahead and parameterize these three line segments. And it's actually pretty easy to parameterize line segments. So here, for 1, we're just going from 0 to 2 in the x. So I'm just going to put 2t in the x and 0 in the y, and let t go from, well, 0 to 1. I'm going to do something similar up here. Here, now the x-coordinate is always 2, and y is going from 0 to 2. So I'll just put 2t in the y direction. And again, that's for t in 0 to 1. And I like to always pick the interval to be 0 to 1 because it's the easiest to work with. Then for 3, now we really got to think about the orientation here. We're starting at the point 2, 2, so we're going to take 2, and then we're ending at the point 0, 0, so we're going to subtract 2t from each coordinate. And then again, let t be in 0 to 1. And so I'll leave it to you to verify that these three vector value functions really do give the parameterizations of these segments. So, as t goes from 0 to 1, this is tracing out this curve, this is tracing out this curve, and this is tracing out this curve. All right, so now that we have a parameterization, we're ready to actually say what our line integral is. It's just the integral, so along this first part, 0 to 1, and then we have f, but now we actually want to plug in what f is, so f is going to be 0, comma 2t, so we have 2t, comma, so the x-coordinate is minus y, so that's 0, and then the y-coordinate is x, which is 2t, and then dot with, actually the derivative of that, this parameterization, which is just 2 comma 0, dt. And now notice, what is this? Well, this is 0 plus 0 in the integrand, so this entire integral is actually 0. So that's awesome. That's one piece out of the way. So the second piece is again just going to be f dotted with the tangential direction, ds. Okay. And so remember that that's actually just f evaluated at the parameterization dotted with the derivative of the parameterization, dt. So again, it's 0 to 1. F evaluated at the parameterization here is going to be, well, minus y, so negative 2t, and then x, which is 2, and then dot with the derivative of the parameterization, which is 0, comma 2, dt. And so what do we get here? We get 0 plus 4. So it's just the integral from 0 to 1 of 4 dt, which is 4. Great. So then the third piece of the curve is going to be f dot t ds, which is, maybe I should write this down in case you're not following. So f dot t ds is really, if I have a parameterization, it's just f of the parameterization dotted with the derivative. So that's what I'm using here in all these examples. Okay, so this is 0 to 1. I have my parameterization, and I just want to plug it in. Now both of the x and y coordinates are the same, so I just want to make one of them negative, so I'll have 2 minus 2t times negative 1 is 2t minus 2, and then 2 minus 2t. So that's f evaluated at the parameterization. And then dot with the derivative, which is negative 2 comma negative 2, the derivative of the parameterization of this curve, dt. But notice what's going to happen. These have opposite signs. These have the same sign. So I'm going to get this plus its negative. So I'm actually just going to get 0 here as well. But now I'm done. So the circulation integral, remember I'm going to put this circle around the integral sign to really signify that this curve, if I call it C, given by 1, then 2, then 3, is a closed, simple, positively oriented curve. And the integral is just the sum of this integral plus this integral plus this integral. So 0 plus 4 plus 0, which equals 4. All right, so now we want to find a flux integral, or a flux line integral, to be more specific. So we have the curve is the unit circle, our favorite curve. So here's x and y. We have the unit circle. Okay, and here's our vector field. And now remember with the flux integral, we're actually doing this contour integral, or just the line integral, over the curve C, where our curve is just the unit circle. X squared plus y squared equals 1. And then I take my force, or my vector field, F, and instead of taking the dot product with the tangential direction, and now notice that this is positively oriented, so the tangential direction would just be along the curve, I'm taking the dot product with the normal direction. And now the normal direction points out of the curve, like this. So this is the normal direction. And of course it's going to depend on the parameterization we get. And we'll need to find a parameterization of the unit circle, but that's really easy. And then the last thing is we integrate with respect to these line elements. And of course this will all fill in when we give the parameterization. So the parameterization of the unit circle, well, hopefully by now you remember this. It's just cosine t sine t. And we'll just let t, we want the entire unit circle, so we'll let t go from 0 to 2 pi. Okay. So the cool thing here is, okay, we want to know what the normal direction is. But if we look at, say, r of t, so this is r of t, so this vector just points to a point on the unit circle, notice that the normal direction points in the same direction as r of t. And this is actually a unit vector. So r of t itself is a unit vector pointing in the normal direction, which is really going to help us out here. So when we do this, we're just going to integrate from 0 to 2 pi. F, we're going to evaluate. So we want to plug in x of t for x. So that's going to be cosine squared t. And then y of t for y, so sine t. And then we take the dot product with the normal direction, but the normal direction is just cosine t sine t. Now that doesn't always work out that nice. Sometimes we have to do a cross product, so like a t cross k. But here we can just observe that, yeah, wow, the normal direction is in the same direction as the position vectors, and it's a unit vector, so we can just use it. So again, this is f of r of t, and this guy is a normal vector as a function of t. And we're just doing the dot product, and we have the parameterization. So everything is looking groovy. And so the other thing that we normally have here that I didn't include is we would really need to replace ds with the magnitude of the derivative. But notice I didn't write anything, or if you want, you can think I'm multiplying by 1 there. Because if I look at the derivative is actually also a unit vector. So it's negative sine t, cosine t, and if I find the magnitude of this vector, I get 1. So here are the kind of the components that go in when I do my parameterization, and there we are. We're good to go. Okay, so what does the integrand become? Well, I'm integrating from 0 to 2 pi, and if I do this dot product, I get cosine cubed t plus sine squared t dt. So I just want to evaluate this integral, and that's going to give me the flux, or in other words, the amount of the field that's going out of this curve. So you can think about like the ripple effect, how much is rippling out of this kind of bounded curve like this. Awesome. Well, there's one thing that we can notice. So if we look at cosine cubed, we're integrating from 0 to 2 pi. And if you've been kind of paying attention, we've seen this a few times in some of the examples, this function has just as much area above and below the x-axis over one period, 0 to 2 pi. So this is actually going to give us 0. And if you don't believe me, it's a simple u substitution to actually compute this, but you do get 0. So this really is equal to the integral 0 to 2 pi of sine squared t dt. Awesome. So now, well, how do we integrate sine squared? Well, this is a trig identity kind of problem. So what we'll do is we'll write this as, well, we have a factor of 1/2, and we get 1 minus cosine 2t. And that's just coming from this identity, sine squared t is equal to 1/2 times 1 minus cosine 2t. Awesome. So again, this cosine 2t, this function has period pi, and we're integrating over 2 periods. So this integral is actually going to be 0. That's a very useful property, in case you are wondering. So all we're doing is just integrating 0 to 2 pi, this part 0 of 1 dt. But this is just 1/2 times 2 pi, or in other words, the total flux is pi.